Hello everyone, in this video we are going to learn about current sources under this circuit theory. Current source. A current source is an active circuit element that is capable of supplying a constant current flow to a circuit regardless of the voltage developed across its terminals. So this is the symbol of the current source. Here it means the current source expressing that current source, the source value or the current value will never change regardless to the voltage across its terminal. So it will never change. This 5 ampere will never change regardless by this terminal voltage. So whatever the terminal voltage is there, this will be constant. This will never change or this will never vary. It will be in the constant form. So here in this circuit diagram, there are two current sources are interconnected in parallelly, 5 amperes, and here this one is also 5 ampere. So these two 5 ampere current sources are connected in parallelly, but this terminal voltage V, so whatever the terminal voltage is doesn't matter here, but it will continuously give the supply of 10 ampere. So here I will explain you later about the parallel connection, series connection or other connection phenomena, but now you have to note down is the current source mean the current source, the supply current will never change or will never vary regardless of the voltage developed across its terminal. Ideal current source. An ideal current source is a two-terminal device which supplies constant current irrespective of load resistance. So this ideal current source should have to supply constant current, but whatever the load resistance is there, it should not be affect the results or the supply current. It should give the supply current continuously. So whatever the load resistance is there, so is there any load resistance, so it should not affect or it should supply constant current irrespective of load resistance. So by observing this characteristic curve, you can see that here the absorbed power should be equal to the delivered power. Okay, let's analyze about the connection of the current sources. Now here current sources connected in parallelly. So here are two current sources are connected in parallelly. This one is 5 ampere, this one is also 5 ampere. But here the I1 will be 5 ampere. Here the I2 will be the same value of I1 which will be equal to 5 ampere. So here I1 will flow through like this. Again the I2 will be flow through like this. But at this point the I1 and I2 will be add together and pass through this path. So here in this path the current will be 10 ampere. So according to the Kirchhoff's current law, here in this node I1 is coming towards the node, I2 is also coming towards the node. Then here this point, at this point the IT or the I will be add with the I1 plus I2. So that will be equal to 10 ampere. Okay, let's analyze about the parallel opposing current sources. So here are two current sources interconnected in parallelly, but the direction of the current sources are in the opposite direction. So you can see that this arrow will indicate the flow direction. So here it is going upward, this is going downward. So the resultant current or the resultant current should be calculated as follow like this. So here you can see that this I1 will be the same value of this current value. Here the I1 will be 5 ampere, I2 will be also the same value of I1, which means 5 ampere. So here in this node, according to the Kirchhoff's current law, the I1 is coming towards the node, I2 is leaving away from the node, and the resultant current I is also leaving away from the node. So here if we use the Kirchhoff's current law for this node, the I1 minus I2 will be equal to I. So the I1 is 5 ampere minus I2 is also the 5 ampere, but it is connected in opposite direction. Therefore minus 5 will be equal to the resultant current. So the resultant current I will be equal to 0 ampere. As the same manner you can analyze the second circuit. So here there are two different current sources are connected in parallelly, and also it is connected in opposite direction. Here this 5 ampere current source is connected upward direction, but this 3 ampere current source is connected in downward direction. So how about the resultant current effect to this circuit? So here you can see that we can use this Kirchhoff's current law in this node. So for this node, if I use the KCL equation, here you can see that for this node there are three terminals. From this path I1 is coming towards the node. From this path I2 is leaving away from the node. Here the resultant current I is also leaving away from the node. So here then is not leaving, we are considering as to leave away from the node. Therefore the resultant current, so we are going to use the KCL. Therefore I1 minus I2 will be equal to I. So here the I1 is 5 ampere minus I2 is 3 ampere. That will be equal to the resultant current I. So the I will be equal to 5 minus 3 equal to 2. So the resultant current will be equal to 2 ampere. So that is what we have mentioned here. Let's move to the series connection. So here in this circuit there are two current sources are connected in series form, but the current value is same value. The direction is also connected in the same direction. Therefore here you can see that this 5 ampere current source is connected in the same direction of this 5 ampere current source. So the resultant current will be the addition of these two values. So the I will be equal to addition. First one is 5 ampere, the second one is also the 5 ampere. Here that is connected is in the same direction of the first one. So plus 5 equal to 10 ampere. So the resultant current will be 10 ampere. Current source example number 1. Two current sources of 250 milliamperes and 150 milliamperes respectively are connected together in parallel aiding configuration to supply a connected load of 20 ohms. Calculate the voltage drop across the load and the power dissipated. So here is our circuit. Here in this circuit you can see that there are two current sources are connected in parallelly. Here this one is 250 milliampere, this one is 150 milliampere. So now the resultant current IT will be equal to, here as I said previously, here we have to add two current sources. Here in this point if we use the KCL, here the I1 is coming toward the node, I2 is coming towards the node. By the resultant current IT we have to consider as to leave away from the node. So according to the KCL, I1 plus I2 will be equal to IT. So the IT we have to calculate. The I1 is 250 milliampere. 250 milliampere mean here we have to convert to ampere. So 250 milliampere equal to 0.25 ampere. So 0.25 ampere plus 150 ampere, sorry 150 milliampere, if we convert into ampere, 0.15 ampere equal to IT. So the IT will be equal to 0.4 amperes. So the second question is the voltage drop across the load. So here is our load. The load is 20 ohm resistor. So to calculate the voltage drop across this load resistor according to the Ohm law, here the VR or the VL will be equal to the current flowing through the load is IT and the resistivity value is 20 ohm. Therefore the IT we know, the IT is 0.4 ampere into 20 will be equal to 8 voltage. So here from this equation we can simply find the VR or the VL. VL means the load voltage. The third question is the power dissipation. The equation to calculate the power dissipation is P is equal to I squared R. So the I is, here the I is IT. Here in our load the power dissipation will be IT squared into R. We know the value IT. IT is 0.4 ampere. So 0.4 squared into R is 20 ohm. So here we have to substitute this 20 ohm. Then that will be equal to 3.2 watt. Ideal and practical current sources. So initially I am going to ask you a question is, so what is ideal current source and what is practical current source? The simple answer is, by observing these two circuit diagram, you can observe it. Here this one is the ideal current source, this one is the practical current source. There is only one difference is, here the RP is infinity. Here there is a value for the RP. So what is that RP? Here the RP is nothing but it is the internal resistance or the terminal resistance of the circuit. So in between these two terminals there will be some value for the terminal resistance or the internal resistance. That's what we call as the internal resistance. That internal resistance should be infinity or there should be a higher value as much as possible. But in the practical life we cannot make it as the infinity value. So there will be some value, but it will be much higher as possible, but there will be a considerable value there for the RP. So that is the main difference for the ideal and practical current sources. So how it is affect to the circuit? So if it is some value, so if it is infinity, so here you can see that for the ideal current source, if the RP is in the infinity, here we can consider as the open circuit connection. Here there is no current path. So we have to consider as the open path connection. So the total value of the current will flow pass through this terminal voltage or the terminal point. So the total 5 ampere will pass through this terminal point. But here in the practical current source, if there are some value, for an example I am considering as RP 1000 ohm, then the current coming from this current source, the IS, from this point, here some small amount of current will pass through this path and the resultant current will be decreased. So here if 5 ampere current pass from the supply, then for an example here 0. Small amount of current will pass through there. That small amount of current as I consider as 0.1 ampere, then the resultant current will be 4.9 ampere. So you can see that in the practical current source there will be some decreases in the value of the current, rated current. So we cannot get the ideal condition. So this is the main difference in between ideal and practical current sources. Practical current source characteristic. So here from this circuit we can plot the characteristic curve like this. So here there are two conditions they have considered. This blue line for the ideal condition, this red line for the real condition. So they have plotted the VI characteristic curve. Here in this diagram you can see that we can't, as I said previously, in the practical life we can't get the exact rated current as the output current. So in the normal practical current sources we can't get the exact value of the rated point. So in the practical life we will get the value will be the less than our rated value. The reason is here IS will come like this, then at this point from this internal resistor there will be small amount of current will pass through this. So the IR, here the IS is coming, here the IR is leaving. So the resultant output current IO will be equal to IS minus IR. According to the KCL, the output current will be equal to IS minus IR. So therefore here in the characteristic curve you can see that here we can't get the exact value of the rated value. Here the IOut will be less than the rated value. So I hope you will clear with this characteristic curve, very easy point. Current source example number 2. A practical current source consists of a 3 ampere ideal current source which has an internal resistance of 500 ohms. With no load attached, calculate the current source's open circuit terminal voltage and the no load power absorbed by the internal resistor. So they are asking at the no load condition, here we have to find the terminal voltage VAB and the power dissipated through this resistor, through this load resistor. So very easy question. Here the IS is 3 ampere. So we have to find the IR. So here at the no load condition there will be no current pass through this point. So here the I output will be 0. There will be no current pass through this space because we have to consider at the no load condition. According to the question, the I output will be 0. Therefore, at this point, according to the KCL, at this point or at this node, according to the KCL, here the IS is coming towards the node. IR is leaving away from the node. IO is 0. So we don't need to consider this IO. Therefore, according to the KCL, the IS minus IR will be equal to I output. I output is 0. Therefore, IS will be equal to IR. So, IS equal to IR equal to 3 ampere. Then the RP is already given 500 ohm. Now we have to find the terminal voltage VAB. To find the terminal voltage, so this terminal voltage will be equal to this terminal voltage. So because this is the parallel connection, very basic theory. So the VAB will be here. The current flowing through this resistor is IR. The value is 500 ohm. We know the value of IR and we know the value of the resistance. Then simply we can find the VAB. Therefore, the VAB will be equal to IR into 500. Then the IR is equal to IS, which means 3 ampere. So 3 into 500 equal to 1500 voltage. So which will be equal to 1.5 kV, kilo voltage. So the VRP or VAB will be equal to 1500 voltage or 1.5 kV. Then we have to find the power dissipation. The power dissipation simply we can find using this equation. P will be equal to I squared R. So the I is here I squared. Here the current is IR. Therefore IR squared. So we know the value of IR. We know the value of R. Then directly the IR is 3 ohm. Therefore the IR squared is 3 squared into 500. That will be equal to 4500 watt. 4500 watt, or another way we can write as 4.5 kilowatt.